Hi. This task is to group up a list of integers by which other integer they are divisible by. So here we start with two lists, and these on the left are the targets, we could say, where that numbers have to be divisible by, and on the right we have our selection of numbers that we're going to test. So the idea is we are returning a vector vectors, or you could say a list of lists. The first list will contain the numbers from the right that are divisible by 2. So that would be the even numbers, 8, 12, and 10. Then the numbers divisible by 4, that's 8 and 12. The ones by 7, that's just 7. The ones that are divisible by 3, which is just 12. And then the ones divisible by 9, which there aren't any. So we need to have an empty list at the end. So we're going to have a list of 5 elements because we have 5 elements on the left. And each sublist then can have up to this many, 6 in this case, elements. But in our case, there won't be any because then we would have to have a 1 on the left. And we can do this quite simply, actually. So we want to do this looping thing. We want to try for each one. So let's make a little lambda that we apply to each one on the right. But we want to apply it not pairwise. That won't work anyway because they have different lengths. We want to apply every time around the loop with the entire right argument as our right argument. So we can do that by pre-processing the right argument with an enclosure. So this makes the right argument into a single element, which is then mapped with each one of the elements on the left. We can try this and see it. So if we just refer to the left argument as alpha, the right argument as omega, then we can see how 2 got paired up with the entire list and 4 got paired up with the entire list and so on. Okay, now we're ready. Now we can start by finding out if divisible or not. We don't have a direct test for that, but we do have a remainder. And if the division remainder is 0, then it's divisible. So this is commonly known as modulus. And so you can see here, this says, yes, this says the remainder when dividing 5 by 2 is 1, dividing 7 by 2 is 1, when dividing 8 by 2 is 0, and over here, when we divide 5 by 4, we get 1 left over, 7, it gives us 3 left over, 8 divides cleanly. So if we just compare these numbers to 0, that will give us a Boolean mask for the ones that are divisible. And all we then need to do is filter the right argument by that mask. So this is a filtering function. It takes a list of ones and zeros on the left, and it takes some data on the right. But this higher order function flips the order of the arguments right and left, such that we get it, our expression, a clean flow from the right to the left of the data. And this gives us the correct answer. We can see that the numbers from the right that are divisible by 2 are the even ones, the ones that are divisible by 4 are 8 and 12, and so on. However, there's also a very clever solution that someone came up with in the chat event leading up to this video, and that used some unusual constructs. Let's have a look at that as well. So let's start up with our numbers here. And the way we're going to do this is we're going to build up piece by piece. First, we're going to start with a divisibility table for all the numbers with all the numbers, because we need to check all of those anyway. And we can do that in one swoop. So we use an outer product, which is kind of like a multiplication table, but instead of using multiplication, we're using the remainder. So this is a remainder table, and we can see that we have 2, 4, 7, 3, and 9 going down, and then 5, 7, 8, 1, and so on going across. And then we can see corresponding numbers, whether they're divisible. So we can see, for example, here that that if we have the third number, which is 7, and we are dividing it into 7, then the remainder is 0, of course, and with 8 we have a 1 over here. And then we can do just like before, comparison with 0, because APL is rank polymorphic, so we can just do comparisons between this scalar and this whole table. And that gives us our divisibility table rather than a modulus or remainder table. Okay, now we need to take each row here and use it to select the corresponding elements from over here. And the way we can do that, there are a couple of different ways we can do it. But we can use a construct with rank. So the rank operator specifies what subarrays we want to be given to a function. So we use the slashes before for the filtering, and then we want to filter using rank 1. And that means we're going to, conceptually at least, loop over every row of these and pair them up with also a rank 1, that's a vector from the right, which is just the right argument. Oops. Yeah, there's a problem here. We need to parenthesize this, otherwise it's not going to work. Okay. Now we can see there's a problem that in order for this to fit into an orthogonal array, then we pad with additional numbers because the length of each of these results isn't the same. So rather than having this be an orthogonal array, we're going to post-process the results from each application of this replicate function, or compress, or filter if you want, with an enclosure to make it into a scalar, make it into its own standalone thing. And that gives us the result that we wanted. Now we can be really clever here. And we do that by realizing that this is actually, what's happening here is actually a pairing up of corresponding rows from the table on the left with everything on the right, and then a concatenation of the individual results. So that really makes sense here, because this is the first result from the filtering, and this is the second result from the filtering, and they're just concatenated together, not joined, but as separate elements, they're joined into a single list. And then we can write that as an inner product. So normally an inner product is the sum of the multiplication. Some people like to call this a map reduce. We start off by mapping with multiplication, and then we do a reduce, which is a summation. But APL generalizes this as a dot. It's also known as a dot product to any two operations that take two arguments. So here, instead of multiplication, we're going to do the filtering, and instead of doing the addition, we're going to do concatenation. This is a very clever insight, and you can look in the description of this video and get a link to the chat transcript where this was discussed for even more details and discussion of it. Now we can simplify things a little bit. We don't actually need parentheses at all around this inner construct. And since we only have a simple thing on the right, but something complex on the left, then if we could swap the arguments of this derived function, this concatenation with filtering inner product, then we could eliminate the parentheses for a nice clean look. So we do that as we did before, and this has long left scope, so it takes the entire thing here and flips it, which means we can get rid of this tech over here and move everything on the from the left to the right and eliminate the parentheses for a beautiful solution. Thank you for watching.